Okay, this should work again. Okay, this is my second recording. First one failed due to technical issues. It was kind of sad. So I'll try this again. Okay, so who am I? I am a former student of Mrs. Becker, the former student, the one she mentioned in one of her YouTube videos. And my name is Hasan. Just call me Hasan. Don't try to give me nicknames, please. Okay, I'm a chemistry major and economics major at Northwestern University. I'm a second year. And right now, I just finished my first quarter of Virgo. Very fun, very great. No sarcasm there at all. So no, I actually like Virgo. So yeah. Okay, so this is my electron formal charge, and I also added a few things about conjugation, and those a few things aren't necessary for the exam, but whatever. I just want to do a thorough and complete presentation. So yeah. So formal charge, special thanks to the College Board for putting on an old AP exam. That's why I can get this presentation. Thanks. And it seems more and more they keep asking about formal charge because they come to the realization formal charge is important in organic, which is a subsequent class you take after general chemistry, which is AP chemistry. So who would have thought that? Not the College Board and me. Whatever. So yeah, that's a joke. Okay. Definition of formal charge is get the pen out, is a charge of an atom would have if each bonding electron pair in the molecule were shared. Point thing is shared. So basically in a molecule and electrons, we'll call that electrons have both this wave and particle-like nature. So it's more like an electron cloud, as they call it. Those physical chemists call it. So yeah, it's important to take note about how electrons are kind of spread out through a molecule. So that's kind of important. And that's what Lewis star structures and structures in general are trying to represent the molecule as best as the way it can, as best as they can to represent the electron density in a succinct way. And that's very important, which you will learn later, that accuracy is important for organic structures. Okay, pen. So yeah, so how to calculate the formal charge? Just this formula, valence electrons. For instance, fluorine is 7, oxygen is 6, and so forth. I don't remember like periodic table exactly. Valence electrons minus 1/2 bonding electrons minus non-bonding. And to really think about it, it's bonding electrons in each bond. Sigma, for instance, a single bond, a sigma bond, has 2 electrons. So 1/2 of that is 1, and that's like one line. A double bond, which is 4 electrons, bonding electrons, which is like sigma to pi bond, has 4, so 1/2 of 4 is 2, so that's like 2 lines. So it's more like valence electrons minus lines minus dots. That's pretty helpful in my opinion. And so the uses, it can tell you which Lewis structure is more dominant, which one is more stable, which one better represents the electron densities around it. And even then with Lewis, even with formal charge and Lewis structures, again, we're making some assumptions, like if all of chemistry, if chemistry is so simple, like I guess you can teach in a year, clearly that's not the case. The more and more chemistry you take, the more you come to the realization that some of the assumptions you make in this class are wrong. You want to come to the realization when going from honors to AP Chem and so forth. Yeah. Okay. So the general rules are you want to have more zero formal charges on atoms. If you there's no way to get all the zeros, then you want us to have the more negative charge, the more electronegative atom, and then to check all the formal charges on the atom should sum up to the overall charge of the molecule. And here's a case example. So this is the phosphate ion. This is Mrs. Becker's handwriting. No surprise here. -3 charge, whatever. And so, if you would assign formal charges, each oxygen would have a -1 charge, so -4. The phosphorus have 5 minus 4, which is 1. So that's -4. So -4 plus 1 is -3. 3 minus, same thing. And you might ask yourself, well, doesn't have all zeros. And so you see here, oh, look at this phosphate. Well, it goes outside the octet. And the answer is that's fine. Atoms cannot expand outside the octet with the first two columns of the periodic table. This is a general rule. That's because of d electrons and everything. And so, yeah, you can't really expand outside the octet with like oxygen or nitrogen or carbon. But phosphorus, which is not in the first two columns of the periodic table, you can. So yeah, just a general rule. Explanation. So this is some calculations. Clearly more zeros. Boom. Now this is okay. This is a old AP exam problem from 2017. No idea how the exam will be this year. I know it was very different, like the last academic year. But this was they're gonna be consistent. They most likely ask maybe about two isomers formic and isocyanic acid. And here's fulminic acid, HCNO. And they ask which is a more accurate structure. And to really answer this question, you have to understand formal charge. And you see here, there's one. So I go carbon, carbon oxygen. So left molecule, right molecule. Well, here the difference is the oxygen -1 here on the carbon -1. We all know that oxygen is more electronegative than carbon. Hence the structure has a -1 on the oxygen, which would be the left structure right here would be that. So yeah. Okay. So that's what I'm saying here. Again, I'm going quite fast, so you can like go back and look at the slides. It's relatively not too bad. It's simple calculations. So yeah. I'm gonna charge CO2, which one is better? This was just like a kind of trivial question because no one I know would draw the CO2 like this. Unless you're having a really bad day, then I guess that's fine. But I wouldn't. So here, +1, 0, -1, 0, 0, 0, more zeros, less zeros. Wow, the structure is better, which is consistent. And if you think about it, this is a bit off because CO2 is nonpolar. So for this, the dipole moments would cancel out here. This one, they won't cancel out, so that's not a good sign. You mess up with your formal charges, maybe. Not even that, but like your intuition would suggest, oh, CO2 is a nonpolar molecule. The dipole moment should cancel out. In part B, the molecule is not symmetrical. So that's like just some intuition. So yeah. Cyanide. Here, this is just some simple calculations. 4, so carbon is 4, 3, 2, 1, -1. So what I'm saying here is, okay, the technical issues. And there's a minus charge on the carbon, not on the nitrogen, to your surprise. This is really important when you take organic chemistry and you do reaction with cyanide, that the attack generally occurs on the carbon, except a few exceptions, but for the most part, yeah, this is true. So yeah, it's important. Okay, yep, just do the calculations, boom. Thought more dominant. So again, you go through the process, find the formal charges, maybe expect something like this on the exam, like maybe, I don't know, like you have three possible loose structures, which one is more dominant? Or even like what are the loose structures, which one is the more dominant, so forth. Okay, so again here, let's go back. Sorry, there's some technical issues. PowerPoint's kind of annoying with Zoom. Okay, so you see here sulfur -1 versus nitrogen -1. Nitrogen is more electronegative than sulfur, therefore this one is better. And that would be the correct answer. Sulfur trioxide, so if you want to think about the octet, so okay, I didn't draw lone pairs in so long. With this, there's a minus formal charge, minus formal charge, minus formal charge, plus 3 formal charge. That's not good. But what if I put a double bond, a double bond, a double bond, and then, if you do that, then you actually get zeros overall. and then, which is good. And that's fine because sulfur is not in the first two rows of the periodic table. So you can expand outside the octet. That's all good. And on the next slide, I believe I show that. See, boom. Oh, and then another comment here. Technically, this arrow implies a reaction. To be honest, there is no reaction going on. It's more like these are resonance structures. To be honest, this resonance structure is not as good as this resonance structure, but they are technically valid resonance structures. Technically, this is moving electrons by definition. That's the definition of resonance. Questions? Most online Zoom. I don't know if you really have any questions. Well, yeah. These are some memes if you're really bored. Look at those. Yeah. So now a disclaimer. This part of the lecture is well beyond AP chemistry. Well beyond. I made this part because it emphasizes the importance of formal charge. And yeah, talking about conjugation and resonance. We were most likely introduced to resonance, I believe, in honors chem. You were introduced again in AP chem. It's mostly wrong. Okay, it's not wrong, but it's not the full picture. And so I want to kind of show more of the picture of conjugation and resonance. So let's consider the phosphate anion. So I drew the more dominant structure with formal charge, but you could just move this double bond around, like move electrons around. These are all valid resonance structures. You might ask yourself, where is this double bond? Where are these electrons in the double bond? On the oxygen, like where are they? And the answer is they would be spread over the entire molecule. And chemists, all chemists generally, would if they're trying to emphasize this idea that it's conjugated, they would draw a resonance hybrid. And so these lines that are the single lines, like these single bonds are filled because as you see here, there's always a single bond with every one, but the double bond is clearly changing. And so you might ask yourself, well, yeah, so these are not fully filled, and you might ask yourself, well, Hasan, this is like -1, 2, 3, 4. Oh well, that's -4, it's -3. And then I would say, you can read the comment, because reading's important. That 3 divided by 4 is 3/4. So you get 3/4 of a negative charge. However, due to like formatting issues and like standard formatting, you can't write 3/4 of a negative charge. So it's generally sent to write minus in a parentheses. So yeah, that's what I would do. Yeah. Conjugation stability. So you might ask yourself, why would a molecule even do conjugation? Is there even a benefit? And the answer is yes. So again, these pi electrons, or the electrons in the double bond, are said to be conjugated. So that means like spread throughout the specific pi system, which in this is the entire molecule. So like resonance structures show that there's conjugation. So if you can draw a resonance structure, it implies conjugation or delocalization of electrons. And so a conjugation is known to increase the stability of a molecule because electrons like being in a large area. Electrons would rather be spread over a large area than in a small region, because that would destabilize it because of electron repulsion. So that's not good. And then this is an important concept, and I'll come back to it later, but molecules will take a certain hybridization and conformation in order to achieve conjugation, whether it be conjugation, hyperconjugation, which I won't cover in this lecture at all. Not at all, because you guys don't understand molecular orbital theory, or whatever. It will take a certain conformation or hybridization in order to do that. So here's a case study, the amide group. I remember you briefly talked about organic chemistry, like functional groups and everything at the beginning of the semester. And so here it is, the amide group. Recall this is the amide group. So these are R groups. These R groups are hydrogens, the primary amide because it's attached to one carbon. Secondary means there's a hydrogen here or here. Tertiary, whatever. And tertiary means like there are 3 carbons attached to the nitrogen. Wow. And so the amide group looks like this, vertices, blah, blah, blah. R is an alkyl, means hydrogen or carbon. And so the thing with the amide group, it's kind of special. It's pretty cool that there's some conjugation that'll occur, and that affects both the rotation about the carbon-nitrogen bond. Recall that sigma bonds have good free rotation, but double bonds don't. But you'll see here that that bond is not a sigma bond, despite this Lewis structure suggesting that. And no one's a carbon oxygen, quote unquote, double bond, like fully double bond, you might predict based on the structure. So yeah. Also the lone pair is optional when doing that. Oh, and these vertices is a carbon. So there's a carbon right here. But organic chemists would never do that. And so okay. So resin structure. So the left structure is more dominant. Is more dominant side. There's a typo. More dominant. I'll fix that later. So these two arrows I put here have a movement of electrons. This is common in organic chemistry, not so much in general chemistry. But generally what this means is the electrons. So a two-headed arrow. Like when I'm saying two-headed, I guess it's a bit weird, but like this, one-headed means one electron. This means two electrons, and so forth. So yeah, these are called curly arrows because they curl. Wow, organic chemists in general are so funny. So, and so I'm just drawing the two resin structures here. So again, this one more dominant, but this one is good insight in talking about. You see this like I mentioned before, this partial double bond characters. Oh, there's a double bond here, there's a sigma bond here. So really, these bonds are not double bonds, purely double bonds or purely single bonds. It's more of a mixture between a double and a single bond. And it's not necessarily halfway in between because oxygen and nitrogen aren't the same atom. It's more like a mixture, like it's more like more than 1.5 for carbon oxygen between carbon and oxygen because oxygen is more electronegative. It's going to pull electron density more there. Nitrogen is like less, it's going to be less electron density, but the idea is like it's not a purely double bond or a purely single bond. Okay. So I put here a 3D diagram of an amide. So I put N-methyl anthenamide, if I'm naming that correctly. There are multiple ways to name these things. But N-methyl anthenamide, so there's a nitrogen, a methyl group attached here, and a methyl group. So this would be like a methyl group. So I'm going to like Me, so methyl, Me, methyl. This is a shorthand. Methyl is CH3, and this is an H. This would be secondary. So this here, but you see here, the whole molecule is planar. You might ask yourself, well, okay, Hasan. We recall that that here, oh look, 1, 2, 3 bonding groups and a lone pair. It should be tetrahedral electron geometry or trigonopyramidal, like molecular geometry according to VSEPR theory. My answer would be VSEPR is wrong. No theory is perfect. And the reason is it doesn't count for conjugation. And even if you want to count VSEPR, these electrons aren't localized on nitrogen. It's spread throughout this nitrogen, carbon, oxygen system, pi system. Pi electrons are moving. So really, this is planar. And it adopts that planar structure because it wants to appear as a stabilizing effect of conjugation. And this is really important for, carboxylic and amide chemistry, like protein chemistry, like, peptide bond is made between carboxylic acid and amide. Like this is very important. So again, it's important. Atoms in conjugation, not the whole molecule. I'm not saying the whole molecule is planar. Clearly, it's not. These methyl groups are not in the same plane. But this carbon, oxygen, nitrogen are all in the same plane. So you need the same plane for conjugation. And so this is a better drawing you see here, right? So why this is so? What's a necessity planarity? It's due to this idea of orbital overlap and conjugation with respect to like orbitals. So like pi bonds, but there's like pi star bonds, molecular orbital theory. And if you have questions, it might be in your textbook. I think it most likely will be your AP chemistry textbook. I'm not sure. I think I have a copy somewhere. But like, it's kind of complicated. Question, you can email me. I'm always free. I mean, I'm busy. I have a life, surprisingly. But yeah, let me ask, why conjugation? What's the importance of conjugation, other than what I've been saying the entire time? So the importance of reactivity. So here's an example, or a few examples. I guess it's more like one example. Recall from acid-base chemistry from honors chem that like acids get protons or hydronium ions or whatever in solution, and then bases remove protons from stuff. So yeah. So yeah, here's an example. So this is a reaction, keep it in mind. Plus or minus H plus means it's under acidic conditions, equilibrium, acid-base equilibrium. Here though, you would think, lone pair, why wouldn't I just put it here? Blah, blah, blah. The answer is conjugation. If that would happen, it could not take that trigonal planar structure, which I was mentioning. You would have to take this like tetrahedral electron geometry, which would remove a conjugation that's highly destabilizing. So it would more protonate on this oxygen. And so if you recall, here that this structure, nope, this one. If you think about here, the negative charge here, it makes sense because you just protonated here. There's negative charge. The electron density is there, which would make sense. Perfect. So again, this idea of using resonance structures to explain reactivity is pretty cool. And so yeah, and so again, this oxygen, carbon, mentioned all planar, all cool. So is this hydrogen, it's all on the same plane. And then those lone pairs are like, the lone pairs here also in an sp2 orbital. So it would be like, about 120 degrees. Yeah, hopefully that makes sense. So this is very complicated, so don't worry if you don't understand this. This is just me having fun. So another examples of conjugation, so carboxylic acid derivative. So in amine is a carboxylic acid derivative. Others are carboxylic acid. So this oxygen, and this oxygen all sp2 hybridized. Because again, what happens is like this can be delocalized. It could do either, or if it's symmetric, it could do one or the other depending on what those R groups are in the acid anhydride and then the ester. Wow, cool. Again, sp2 hybridized, you need sp2 hybridized for planarity, conjugation, so forth. And so, yeah. So I wanted to bring this up because like many people fear organic chemistry, think it's really hard. It's different than gen chem 100%, but it's kind of cool in terms of how reactivity molecules work and stuff like that. It creates a certain intuition that hopefully you can build in this class. I think I built in this class and it prepared me well at Northwestern. Northwestern is a very, very good school for chemistry, like top 5 in the nation, in my opinion. Even the best for graduate school. They're very good for undergrad, very hard. In fact, Mr. Bucker prepared me well as a testament of her teaching ability. So yeah. So email me at this email if you have any questions. Questions, anything in general, like college. Like there most likely might be some seniors in this class, or even juniors thinking about college. Ask me. I know some stuff about college. I'm surprisingly a college student, despite how I look. I look like I'm 15, but whatever. That's cool. Yeah, thanks for listening and watching and whatever. I hope you have a good day. And I think everything is good here. Yeah, thank you.